Welcome to the Late Lab. It's good to have you here. Before the universe starts behaving in ways that feel frankly unreasonable, take a moment to settle in. Maybe tonight finds you in a dark room with only the edge of a screen lighting the wall. Maybe you are listening while the house has gone quiet, with the ordinary world finally doing the decent thing and leaving you alone for a while. Or maybe you are somewhere less peaceful, borrowing a little calm from the background noise. Wherever you are, this is a good place to slow down. The day can stay outside the door for a bit. For the next little while, attention can drift toward one of the strangest questions in modern physics, not with urgency, but with curiosity. If you enjoy these slow journeys through science, a like and subscribe helps the Late Lab continue to glow away in its small corner of the night. And if you are already subscribed, thank you. Truly, every bit of support helps keep these quiet explorations going. Tonight's question is simple enough to say, and surprisingly difficult to answer. Why does reality become one thing? Quantum physics does not always describe the smallest parts of nature as settled little objects with neat little facts attached to them. Before measurement, a particle may be described through a range of possible outcomes. Not because the theory is being vague, and not because the particle is shy, although quantum physics does often give that impression. It is because the most accurate description science has found is built around probabilities, wave functions, and possibilities that do not behave like ordinary hidden details waiting politely to be discovered. Then a measurement happens. A detector clicks, a mark appears, a number is recorded. Out of all the possible answers the theory allowed, one answer becomes the answer. The world does not present a menu of outcomes. It gives one result, sits back, and behaves as though this was perfectly normal. This is the quantum measurement problem. It is not just a spooky side note or a philosophical decoration placed on top of the real science. It reaches into the heart of what quantum mechanics says about nature, information, observation, probability, and the strange border where the microscopic world becomes the familiar world of clocks, chairs, coffee mugs, and other objects that generally know how to behave themselves. So let's begin. When quantum possibilities are measured, why does only one reality seem to remain? The world usually does a very good impression of being definite. A mug sits on a table, a door is open or closed, a lamp is switched on or off. The moon is in one part of the sky rather than several polite alternatives at once. Ordinary reality arrives with crisp edges. It may be complicated, messy, noisy, and occasionally full of misplaced keys. But it does not usually seem undecided about what it is doing. A tennis ball flying through the air appears to have a position, a speed, and a path. A raindrop sliding down a window has a location that can be pointed to. A book on a shelf does not seem to be waiting for a measurement before choosing whether it is there. In everyday life, observation feels almost passive. A person looks, and the world is simply found. Quantum physics quietly disturbs that comfortable picture. At the smallest scales that have been carefully studied, nature is not always described as a collection of tiny objects carrying neat little facts around with them. An electron is not simply treated as a miniature bead with a perfectly known position waiting to be discovered. A photon is not always described as taking one ordinary path through space before anyone checks. Instead, quantum mechanics often describes a system through a range of possible outcomes. The theory does not always say, in the familiar classical sense, that the particle is definitely here, definitely there, and definitely moving in one precise way. It gives a mathematical description of what could be found if a measurement is made. That description is called the wave function. The wave function is one of the central ideas in quantum mechanics. It is not a little physical mist that can be photographed drifting around an atom like a microscopic weather report. It is a mathematical object used to describe the possible states of a quantum system and to calculate the probabilities of different measurement outcomes. When handled correctly, it is astonishingly accurate. It helps explain why atoms are stable, why materials behave as they do, why light comes in individual packets called photons, and why modern devices can use quantum effects with extraordinary precision. Yet it also leads straight to a deep question. If the wave function can describe many possible outcomes, why does a measurement produce only one? A detector does not usually show a delicate menu of maybes. It clicks in one place. A photographic plate records one mark. A laboratory instrument displays one reading. A screen shows one spot of light, not all possible spots at once. The mathematics may describe a spread of possibilities, but the experienced world gives a single result. Reality, at least from inside ordinary experience, becomes one thing. This is the quantum measurement problem. The puzzle is not simply that quantum mechanics involves probability. Probability is familiar enough. A coin toss has probability. A dice roll has probability. Weather forecasts have probability, and occasionally the weather appears to enjoy proving the forecast wrong with a certain theatrical flair. But in many ordinary cases, probability is usually treated as a sign of incomplete knowledge. The coin already lands one way. The dice already settles on one face. The raindrops already exist in one pattern. The uncertainty belongs mostly to the observer. Quantum probability is stranger than that. In standard quantum mechanics, even the most complete description of a system does not always assign one definite value to every property before measurement. The wave function gives probabilities for what may be found, and those probabilities are not just a temporary failure of human bookkeeping. They are built into the structure of the theory itself. Measurement, then, becomes far more interesting than simply looking. In quantum physics, measurement does not have to mean a human being staring intensely at a particle, perhaps making the particle feel awkward. A measurement is any physical process that produces a stable record of an outcome. It may be a detector click in a particle experiment. It may be a tiny mark on a photographic plate. It may be an electrical signal stored in a laboratory device. It may be information copied into the surrounding environment in a way that can, at least in principle, be checked later. This matters because the word observer has caused a great deal of confusion. Quantum measurement is often described in popular culture as if consciousness reaches into the universe and forces it to decide what it wants to be. That is not the careful scientific picture. Human awareness may be involved when a scientist later reads a result, but the physical process of measurement begins long before anyone forms a thought about it. A detector can register a particle in an empty room. A camera can record a photon without anyone watching the camera at that moment. The record is physical. So the real question is not whether a mind magically summons reality into existence. The real question is how a quantum system, described by possible outcomes, becomes linked to a measuring device, an environment, and a lasting record that contains one outcome rather than another. That is already strange enough. No extra fog machine is required. The measurement problem sits at the border between two ways of describing the world. On one side is the smooth quantum evolution of the wave function, where possible outcomes can coexist in a structured mathematical description. On the other side is the definite world of recorded facts, where an experiment produces a result that can be written down, repeated statistically, shared with other scientists, and used to build technology. Somewhere between those two descriptions, possibility becomes fact. The word becomes must be used carefully here. Different interpretations of quantum mechanics disagree about what is really happening. Some approaches say the wave function collapses into one result. Some say there is no collapse, only branching histories. Some say particles always had definite positions guided by a deeper wave. Some suggest that collapse may be a real physical process that happens under certain conditions. The experiments work, the predictions are reliable, the meaning remains unsettled. That is what makes quantum measurement so fascinating. It is not a gap created by sloppy thinking, and it is not a mystery invented because scientists forgot to check under the sofa cushions of reality. It appears inside one of the most successful scientific theories ever developed. Quantum mechanics predicts the behavior of atoms, particles, light, semiconductors, lasers, and magnetic resonance with astonishing success. The theory is not fragile. It is almost annoyingly good. And yet, when asked what exactly happens during measurement, the answer becomes less simple. A tiny quantum system may be described through several possible results. A larger measuring device produces one visible record. The surrounding world reinforces that record until it becomes part of ordinary reality. The click happened, the mark appeared, the number was stored. The world moved forward with one fact added to it. This is the quiet tension at the heart of the title. Reality seems to become one thing when measurement turns a cloud of possible outcomes into a definite event. Not necessarily because a person looks, and not because nature is being mystical for dramatic effect, but because physical interaction, probability, information and interpretation meet at the same strange doorway. Before quantum physics, measurement seemed simple. Something had a property, and an instrument revealed it. After quantum physics, that old assumption could no longer be taken for granted. The act of measurement was no longer just a way of learning about reality. It became part of the question of how reality presents itself as definite in the first place. That is why the ordinary world is the right place to begin. Chairs, clocks, mugs, lamps, and falling raindrops all seem settled. They give the impression of a universe made of clear facts. But beneath that familiar surface is a deeper theory in which possible outcomes are not merely hidden behind a curtain. They are woven into the mathematical language of nature. The mystery is not that the everyday world disappears. It plainly does not. The mystery is that the everyday world appears so definite when its smallest ingredients are described by a theory of probabilities, wave functions, and measurement outcomes. Reality becomes one thing. The question is, how? Before quantum physics made measurement feel strange, physics had built a very different kind of world. It was a world of positions, speeds, forces, paths, and causes. A stone fell because gravity pulled it downward. A planet moved because the sun's gravity held it in orbit. A cannonball followed a curve through the air because its motion could be broken into forward movement and downward acceleration. Everything seemed to happen in a way that was difficult, perhaps even impossible, to calculate perfectly in practice, but still definite in principle. The old picture was not vague. It was beautifully confident. In classical physics, an object had a position whether or not anyone looked at it. It had a speed whether or not anyone measured it. A planet on the far side of the sun did not need a telescope pointed at it in order to continue politely orbiting. The moon did not wait for astronomers to check its appointment book before deciding where to be. Reality was assumed to possess its facts already, and measurement was simply the act of finding them. That older certainty was shaped more than anyone else by Isaac Newton. In 1687, Newton published Mathematical Principles of Natural Philosophy, usually known by its shortened Latin title, Principia. It became one of the most important works in the history of science. Newton's laws of motion described how objects move when forces act on them, and his law of universal gravitation described the attraction between masses. With the same basic framework, physicists could understand falling objects on Earth and the motion of worlds in the sky. This was a startling unification. The apple and the moon were no longer separate kinds of mystery. They belonged to the same physical story. The apple fell toward Earth, and the moon continually fell around Earth, moving forward fast enough that it kept missing the ground. That is a wonderfully elegant idea, and also a useful reminder that the moon has spent billions of years failing to crash with impressive consistency. Newton's physics made nature look mechanical. Not mechanical in a crude or lifeless sense, but mechanical in the sense that one state of motion led into another according to clear rules. If the position and velocity of an object were known, and if the forces acting on it were known, then its future path could be predicted. The motion of tides, pendulums, projectiles, planets, and comets could all be described with an accuracy that earlier generations would have found almost unreal. This way of thinking reached one of its most famous expressions through Pierre-Simon Laplace. Laplace imagined, in principle, an intellect that knew the position and motion of every particle in the universe, along with all the forces acting between them. Such an intellect would be able to calculate the entire future and reconstruct the entire past. This idea later became known as Laplace's demon, although the name sounds rather more theatrical than the mathematics required. The point was not that Laplace believed in an actual demon lurking behind a chalkboard. The point was that classical physics suggested a universe whose future was already contained in its present, like a vast clockwork mechanism unfolding moment by moment. In this view, uncertainty came from ignorance. If a person could not predict the exact weather, the problem was not that the atmosphere had no definite state. It was that the atmosphere was too complicated to measure and calculate completely. If a coin toss looked random, the coin was still assumed to follow a definite path through the air, shaped by its spin, speed, angle, air resistance, and the surface it landed on. The randomness belonged to limited knowledge, not to nature itself. Then, James Clerk Maxwell extended this sense of lawful order into light, electricity, and magnetism. In the 19th century, Maxwell showed that electricity and magnetism were not separate curiosities, but connected parts of one electromagnetic field. His equations described how changing electric fields produce magnetic fields, and how changing magnetic fields produce electric fields. They also revealed that light itself could be understood as an electromagnetic wave travelling through space. This was one of the great achievements of classical physics. Candles, lightning, magnets, radio waves, sunlight, and electrical circuits became part of a single continuous theory. Maxwell's work did not make the universe feel less orderly. It made it feel more deeply ordered. Even invisible fields seemed to obey precise laws. Light did not need to be treated as a supernatural glow or a mysterious substance. It became a wave in the electromagnetic field, moving with a definite speed and described by elegant mathematics. Classical measurement made sense inside this world. A ruler measured a length that was already there. A clock measured a time interval that had already passed. A thermometer revealed a temperature that belonged to the system before the reading was taken. A telescope collected light from a distant object and allowed its position to be inferred. A scale measured weight. A barometer measured air pressure. None of these acts seemed to create the property being measured. They only revealed it, sometimes imperfectly, sometimes with experimental disturbance, but always with the assumption that the property existed beforehand. This assumption is so natural that it still shapes everyday thinking. A door is not thought to become open because somebody checks it. A mountain does not acquire a height because a surveyor arrives with instruments. A train does not choose its speed when a speedometer reports it. The world appears to carry its properties independently, and observation simply catches up with them. For most ordinary purposes, this classical picture works extremely well. It sends spacecraft across the solar system. It explains bridges, engines, falling objects, ocean tides, sound waves, lenses, gears, and the flight of a thrown ball. Engineers still use classical mechanics constantly because, at human scales, its predictions are often more than accurate enough. Classical physics was not thrown away when quantum theory arrived. It remains one of the most successful approximations ever discovered. The problem was that the universe is not only made of falling apples, swinging pendulums, and planets with excellent timing. It is also made of atoms, electrons, photons, nuclei, and fields, behaving at scales far below ordinary sight. Human senses did not evolve to notice the detailed behavior of single particles or the emission of individual quanta of light. The everyday world is not false, but it is a softened, averaged, large-scale view of something deeper. At those smaller scales, the comfortable assumptions began to fail. Light did not always behave like a smooth, continuous wave. Energy did not always flow in any amount whatever. Atoms did not radiate energy in the way classical physics expected. Electrons did not behave like tiny planets neatly circling a nucleus. Experiments began to show that the old belief in definite properties waiting quietly to be uncovered could not simply be carried downward into the quantum world. That is why quantum measurement was so disturbing. It did not merely add a few new particles to the old picture. It challenged the meaning of measurement itself. In classical physics, measurement uncovered a fact. In quantum physics, measurement seemed tangled up with the appearance of a fact. The older world said that reality already had one clear answer, whether or not anyone checked. The quantum world suggested that, in some situations, the theory could only give a range of possible answers until a measurement produced one actual result. Classical physics gave reality the feeling of a finished sentence. Quantum physics revealed that underneath, nature sometimes looks more like an unfinished question. The old classical picture did not fall apart, because physicists grew bored and decided the universe needed more personality. It began to crack because experiments kept returning answers that did not fit the rules everyone trusted. At first, the problems looked small, a little issue with the colour of heated objects, a strange detail about light knocking electrons from metal, sharp lines appearing in the colours emitted by atoms. Tiny puzzles, really, if a universe can have tiny puzzles. But each one pointed toward the same uncomfortable idea. At the smallest scales, nature was not behaving like a smooth classical machine. One of the earliest cracks came from blackbody radiation. A blackbody is an ideal object that absorbs and emits radiation perfectly, and physicists wanted to understand the pattern of light given off by hot objects. A piece of metal heated in a fire begins to glow red, then orange, then white as its temperature rises. Classical physics could explain some of this behavior, but when it tried to predict the full pattern of radiation, especially at shorter wavelengths, the mathematics went badly wrong. This failure became known as the ultraviolet catastrophe. The name sounds like a very dramatic weather report, but the problem was real. Classical theory predicted that a hot object should emit absurdly large amounts of energy at ultraviolet wavelengths. Real objects did not do this. The laboratory results were calmer than the theory, which is not usually what a physicist wants to hear from the universe. In 1900, Max Planck found a way to match the observed data. His solution was strange. He proposed that energy was not exchanged in any amount whatsoever, as classical physics had assumed, but in small discrete packets. Energy came in countable steps. Planck did not immediately overturn all of physics in a single triumphant moment. He was trying to solve a specific problem. But his work introduced one of the key ideas that would become quantum theory. Nature, at small scales, could be grainy rather than perfectly smooth. Then came the photoelectric effect. In this experiment, light shines on a metal surface and electrons are emitted from it. Classical wave theory suggested that brighter light should eventually give electrons enough energy to escape, no matter the colour of the light, as long as enough energy arrived. But experiments showed something different. Below a certain frequency, light would not eject electrons at all, even if it was intense. Above that frequency, electrons could be released immediately, even when the light was weak. In 1905, Albert Einstein explained this by treating light as if it arrived in individual quanta of energy. These light quanta were later called photons. The energy of each photon depended on the frequency of the light. A single photon of high enough frequency could knock an electron free. A flood of lower frequency photons could not, because each individual photon still lacked the required energy. The metal was not waiting patiently for a pile of weak light to save up. It needed the right kind of packet. This changed the meaning of measurement in a quiet but serious way. Experiments were no longer just revealing smooth flows of energy. They were recording individual exchanges. One photon absorbed, one electron emitted, one event counted. Atomic spectra created another problem. When atoms are heated or excited, they do not emit every colour smoothly. They emit light at specific wavelengths, producing sharp spectral lines. Hydrogen, the simplest atom, showed a clear pattern of lines that classical physics could not explain. If electrons moved around the nucleus according to ordinary classical rules, atoms should have behaved very differently. In fact, classical electromagnetism suggested that orbiting electrons should radiate energy continuously, spiral inward, and collapse into the nucleus. Ordinary matter should not be stable. This is a fairly serious issue, since matter continuing to exist is one of its better qualities. In 1913, Niels Bohr proposed a model of the atom in which electrons could occupy only certain allowed energy levels. They could jump between these levels by absorbing or emitting specific amounts of energy. This helped explain the sharp spectral lines of hydrogen. The atom was not a tiny solar system with electrons moving through any orbit they liked. It had permitted states, and the light it emitted came from transitions between those states. Planck, Einstein and Bohr did not yet solve the quantum measurement problem. They did not fully explain why a spread of possible outcomes becomes one recorded result. But their work forced physics toward a new view of nature. Energy could be exchanged in discrete units. Light could behave as individual photons. Atoms could possess fixed energy levels. Events at the smallest scales were not always continuous, smooth or classically definite. The old confidence had not vanished, but it had been wounded by evidence, not by speculation, not by philosophical mischief, by furnaces, metals, prisms, atoms and measurements that kept saying, very politely, no. Classical physics had imagined measurement as the uncovering of properties that were already there in the familiar way. These early quantum discoveries made measurement feel more delicate. A detector might register a single photon. An atom might emit one precise colour of light. An electron might be released from metal only if the incoming light arrived with enough energy per photon. The world was beginning to look less like a continuous flow and more like a sequence of individual physical events. And once physics accepted that nature could behave in countable steps, the next question became unavoidable. If the small world gives results one event at a time, what decides which event actually happens? The early quantum discoveries had shown that nature could be strangely countable. Energy could be exchanged in packets, light could arrive as photons, atoms could emit only certain colours. The smooth classical picture had not disappeared, but it had begun to look like a large-scale approximation, a beautifully useful surface covering something more unfamiliar underneath. The next step was even stranger. It was not enough to say that light sometimes behaved like particles. In 1924, Louis de Broglie proposed that matter itself could have wave-like properties. This meant that electrons, which had been treated as particles of matter, might also be associated with waves, not waves made of water, and not little ripples sloshing around inside an atom like a microscopic bath. These were matter waves, connected to the motion and behaviour of quantum objects. De Broglie's idea was bold because it extended wave behaviour beyond light. If light could behave like particles, perhaps particles could behave like waves. This symmetry was elegant, but it was not just decorative. Electron diffraction experiments soon showed that electrons really could produce wave-like patterns when scattered by crystals. Matter, at its smallest scales, was not behaving like a collection of tiny billiard balls moving along neat paths. It had a wave character built into it. Then Erwin Schrödinger gave this idea a powerful mathematical form. In 1926, he introduced the Schrödinger equation, the central tool for describing how quantum wave functions change over time. The equation allowed physicists to calculate the behaviour of quantum systems with remarkable precision. Atoms, electrons, and other microscopic systems could now be described not by ordinary paths alone, but by wave functions that evolved according to strict mathematical rules. The wave function became one of the great symbols of quantum mechanics, although the word symbol makes it sound simpler than it is. It does not describe an electron in the same way that a map describes a car's route down a road. A car can be imagined taking one path, whether or not a person happens to know it. A wave function is different. It contains the information needed to calculate the possible outcomes of measurements. It is a mathematical description of what may be found and how likely those findings are. Max Born made this interpretation clear. In 1926, Born proposed what is now called Born's rule. The wave function, he argued, should be used to calculate probabilities for measurement outcomes. This was a major shift. The wave function was not simply showing a fuzzy little object moving through space. It was giving a map of likelihoods. This is where possibility entered physics in a deeper way. An electron in an atom, for example, is not described as a tiny planet moving around the nucleus on a neat track. Instead, its wave function can describe where the electron is likely to be found if a measurement is made. Some regions may be more probable, others may be less probable. The electron's position is not usually pictured as a hidden classical fact, waiting quietly under a dust sheet. The quantum description itself gives a spread of possible results. A photon can be described in a similar way when it has more than one possible path. The wave function may include different routes that can interfere with one another, almost as if possibility itself has a structure. This is one reason quantum theory feels so different from everyday intuition. In ordinary life, probability often means that something definite has happened, but the details are unknown. The card is already in the envelope, the coin has already landed, the missing keys are already somewhere, probably in the most irritating place available. Quantum probability is not always like that. In standard quantum mechanics, even the most complete description of a system can still predict only a range of possible measurement outcomes. The uncertainty is not merely a failure of eyesight, clumsy instruments, or poor bookkeeping. It is part of the theory's deepest structure. That does not mean quantum physics is vague. In fact, it is astonishingly precise. Born's rule does not allow any random guess to count as science. It gives exact probabilities that can be tested across many repeated experiments. A single event may not be predictable with certainty, but the pattern of many events can be predicted with extraordinary accuracy. Quantum mechanics is not a shrug, it is a very disciplined form of uncertainty. The difficulty is that definite experience does not feel like a probability map. A detector does not register all the possible places an electron might appear. It registers one. A screen does not show every possible photon path as an ordinary visible result. It shows a mark, a flash, a recorded event. The wave function can contain several possible states, but measurement gives a single outcome. This is the unsettling gap at the center of quantum measurement. The theory describes possibility with great accuracy. Experience presents actuality with great confidence. The world of the wave function is broad, structured, and probabilistic. The world of measurement is narrow, definite, and recorded. The scattered cracks in classical physics had become something much deeper. Nature was not merely refusing a few old predictions. It was asking for a new language, one in which possibility was not just a sign of ignorance, but part of the formal description of reality itself. The wave function gives quantum physics its strange landscape of possibility, but the strangeness becomes much easier to feel when those possibilities are allowed to meet. This is where superposition enters the story. In quantum mechanics, superposition means that a system can be described as a combination of possible states, rather than being limited to one settled state in the ordinary classical sense. An electron may not simply be described as here or there before measurement. A photon may not simply be described as taking one path or another. The wave function can include several possibilities at once, and these possibilities can influence the final pattern of results. That is already unusual, but it becomes far more revealing when the possibilities overlap and interfere. The most famous way to see this is through the double slit experiment. Its basic shape is simple enough to imagine. A source sends light, or electrons, toward a barrier with two narrow openings. Beyond the barrier is a screen where the final impacts or bright regions can be recorded. If ordinary particles were simply travelling like tiny pellets, it would be natural to expect two bands on the screen, one behind each slit. Some particles would pass through the left opening, some would pass through the right opening. The screen would show two main regions of arrival, and everyone could go home early, which physicists almost never do. But waves behave differently. When a wave passes through two openings, each opening becomes a new source of spreading wavefronts. These wavefronts overlap. In some places they reinforce each other, making a stronger effect. In other places they cancel each other, making a weaker effect. This creates an interference pattern, a sequence of bright and dark bands, or high and low probabilities. Thomas Young demonstrated this kind of interference with light in the early 19th century. His double-slit work helped show that light had wave-like behaviour. This was a major moment in the history of optics, because it gave strong evidence against a purely particle-like picture of light. Light, it seemed, could spread, overlap, and interfere like a wave. Quantum physics later made the same idea much stranger. When electrons are sent through a double-slit arrangement, they can also produce an interference pattern. This is not what classical intuition expects from bits of matter. Electrons were supposed to be particles, and particles were supposed to go through one opening or the other. Yet experiments showed that matter could behave in a wave-like way. Clinton Davison and Lester Germer helped confirm this in 1927 when they observed electron diffraction from a nickel crystal, giving powerful evidence for the wave nature of electrons. The unsettling part is that the interference pattern can build up even when particles are sent through the apparatus one at a time. Each individual electron is detected as one event, a single mark on the screen. But after many electrons have been recorded, the full pattern looks like the result of wave interference. It is as if each electron is described by possibilities that pass through both openings and then interfere, even though the final measurement gives only one detected spot. This is why the double slit experiment sits so close to the measurement problem. Before measurement, the quantum system is described by a wave function containing multiple possible paths. When no attempt is made to find out which slit the particle travels through, the possibilities can interfere and produce the familiar pattern of bands. But if a detector is placed to determine which slit the particle passes through, the interference pattern disappears. The results become more particle-like. The key point is not that the particle is embarrassed by being watched. The detector does not need a human personality looming over it with a clipboard. The important change is physical. The particle becomes linked to a measuring device, and information about the path becomes available in the world. Once that which path information exists, the delicate interference between alternatives is lost. Richard Feynman famously described the double slit experiment as containing the central mystery of quantum mechanics. That does not mean every part of quantum theory can be reduced to one classroom diagram, but it does mean the experiment captures the deep tension with remarkable clarity. The wave function allows possibilities to combine. Measurement produces definite records. Between those two facts lies the puzzle. The double slit also shows why the wave function cannot be dismissed as empty bookkeeping. If it were only a convenient way to describe ignorance, it would be hard to explain why the possible paths produce a real interference pattern. The structure of the wave function affects what appears on the screen. The probabilities are not casual guesses. They have shape, order, and consequences. At the same time, the final outcome remains stubbornly definite. A single electron does not arrive as a visible smear across the entire screen. It leaves one mark. A photon does not flash everywhere it might have gone. It is recorded in one place. The wave-like description spreads through possibility, but the measurement arrives as an event. This is the quiet drama of superposition. Not a loud contradiction, but a careful mismatch between the way quantum systems are described before measurement and the way results appear afterward. Before measurement, the system can be represented as a combination of possible states. After measurement, one result is found. The double slit does not merely say that quantum physics is weird, it shows exactly where the weirdness enters. Possibilities do not just sit invisibly in the background. They can overlap. They can interfere. They can shape the pattern of reality before a measurement is made. Then the detector clicks, and the world gives one answer. The double slit experiment made a quiet but stubborn demand. It asked physics to explain why the same quantum object could behave as though several possibilities were available, and yet still appear as one definite event when measured. This was not a small adjustment to the old picture. It was not like discovering that a planet was a little heavier than expected, or that a measurement needed a better ruler. It suggested that the kind of question asked of nature could shape the kind of answer nature gave back. Light and electrons did not simply arrive with one ordinary description already attached. In some arrangements, they revealed wave-like interference. In others, they appeared as individual particle-like events. The experiment did not merely confuse the furniture of physics. it rearranged the room. Niels Bohr became one of the central figures trying to understand this new situation. His idea of complementarity was an attempt to describe the strange way quantum systems can show different aspects depending on the experimental arrangement. A photon can behave in a way that reveals wave-like interference, or it can be detected as a single particle-like event. An electron can produce diffraction patterns, yet it can also strike a screen as one localized mark. These are not simply two ordinary pictures waiting to be combined into one comfortable image. They are complementary descriptions, each necessary in its proper experimental context, but not both fully available in the same classical way at once. Complementarity does not mean that quantum objects are just indecisive little things changing costumes backstage. It means the classical words wave and particle are limited tools. They come from everyday experience, from water ripples, thrown stones, sound waves, beams of light, and other familiar behavior. Quantum systems are not required to fit neatly inside those older categories. The experiment decides which aspect becomes visible. Werner Heisenberg approached the same new world from another direction. In 1927, he introduced the uncertainty principle, one of the defining ideas of quantum mechanics. It states that some pairs of properties cannot both be given perfectly definite values at the same time. The most famous pair is position and momentum. Position describes where something is. Momentum describes how much motion it carries, depending on its mass and velocity. In quantum mechanics, the more sharply a particle's position is defined, the less sharply its momentum can be defined, and the reverse is also true. This is often misunderstood as a problem caused by crude measurement. It is tempting to imagine someone trying to look at an electron, shining light on it, bumping it slightly, and ruining the measurement like a clumsy person knocking a cake while trying to photograph it. There is a little historical reason for that image, because Heisenberg himself used microscope-like examples when explaining the idea. But the deeper uncertainty principle is not just about careless instruments disturbing delicate particles. It is built into the mathematical structure of quantum theory. Position and momentum are not merely two hidden facts waiting to be revealed if only the laboratory were tidy enough. In standard quantum mechanics, they are connected to the wave-like description of the system itself. A wave that is tightly confined to a small region is made from a broader spread of momenta. A wave with a very definite momentum is spread out more widely in position. The limitation belongs to nature's quantum description, not simply to human awkwardness. This mattered enormously for the meaning of measurement. In classical physics, a measurement was usually thought to uncover a pre-existing property. A planet had its position, a thrown stone had its speed, a clock had its reading. If the measurement was imperfect, that was a practical problem. Better tools could, in principle, reveal the fact more accurately. Quantum mechanics did not allow that old confidence to survive unchanged. In some cases, the theory did not assign perfectly definite values to every property before measurement. Instead, it gave probabilities for possible results. A measuring arrangement could reveal one kind of information, while making another kind unavailable. The result depended not only on the system, but on the whole physical context in which the question was asked. The Copenhagen interpretation grew out of this atmosphere. It is associated mainly with Bohr, Heisenberg, and the early development of quantum mechanics, although it should not be imagined as one perfectly uniform doctrine written on a single neat page. Different physicists use the phrase in different ways, and even Bohr and Heisenberg did not always express the ideas identically. Still, the broad Copenhagen view treated quantum theory as a theory about what can be said and predicted from experimental arrangements and measurement results. In this view, The wave function gives the probabilities of possible outcomes. Measurement is the special event in which one definite outcome is obtained. Before measurement, the quantum system is described by a range of possibilities. After measurement, the experiment has a recorded result. The detector clicks here rather than there. The particle is found with this value rather than that one. The possible becomes actual, at least within the laboratory description. This approach was powerful because it worked. It gave physicists a practical way to use quantum mechanics without pretending the microscopic world was just a smaller version of the classical world. It told them how to calculate, how to prepare experiments, how to predict probabilities, and how to connect theory with observations. In laboratories, that mattered. Physics is not only a search for comforting pictures. It is also the discipline of asking nature careful questions and accepting the answers, even when the answers arrive wearing very unusual shoes. Yet the Copenhagen view also left a deep unease. It described how probabilities connect to measurement outcomes, but it did not fully explain what physically happens when measurement occurs. Where exactly does the quantum description end and the definite classical record begin? Is collapse a real physical event, or a change in knowledge? What counts as a measuring device? Why should the smooth evolution of the wave function be interrupted by the act of measurement? These questions did not make quantum mechanics weak. They made it fascinating. Bohr and Heisenberg gave physicists a language for surviving the double slit and many other experiments. They showed that the old classical demand for one complete picture, with every property definite at all times, could not simply be imposed on the quantum world. The cost was clarity of a different kind. The mathematics worked. The experiments agreed. The world could be predicted with astonishing accuracy. But behind every detector click remained the same quiet puzzle. A quantum system can be described by possibilities, and measurement gives one result. The Copenhagen view accepted this as a central feature of physics. It helped science move forward. It also left reality standing at the edge of a question, looking definite, but no longer quite as simple as it had once seemed. The Copenhagen view gave physicists a practical way to work with quantum mechanics, but it left a quiet line running through the theory. On one side was the quantum system, described by a wave function and a spread of possible outcomes. On the other side was the measuring apparatus, producing one definite result. The question was where, exactly, that line should be drawn. John von Neumann gave this problem one of its most careful early forms. In 1932, he published Mathematical Foundations of Quantum Mechanics, a work that treated quantum theory with a new level of formal precision. Von Neumann was interested in what actually counts as a measurement, not in the casual sense of looking at a dial, but in the deeper physical sense of connecting a quantum system to a device, a record, and eventually a known result. This connection is often called the measurement chain. Imagine a radioactive atom that may decay. Before the measurement, quantum theory may describe it through a set of possible outcomes. It may have decayed, or it may not have decayed, with certain probabilities attached to each possibility. A Geiger counter is placed nearby. If radiation is emitted, the detector registers it. A click is produced. A signal moves through the instrument. A needle shifts. A number changes, or a digital record is stored. The event becomes part of the larger world. At first, this seems simple. The atom did something, and the instrument noticed. But quantum theory makes the story more slippery. The Geiger counter is also made of atoms. Its wires, gases, circuits, and display are all physical systems built from quantum matter. If quantum mechanics applies universally, then the measuring device should not sit magically outside the rules. It should also be describable, at least in principle, by a larger wave function. That is where the measurement chain becomes troubling. The atom interacts with the detector interacts with its circuitry, the circuitry interacts with the display interacts with the surrounding environment. Eventually, a person may read the result and write it down. But if every link in the chain is physical, and every physical thing is made of quantum systems, then where does the definite outcome enter? Wave function collapse is the traditional name for the apparent transition from a spread of possible outcomes to one observed result. Before measurement, the wave function may describe several possibilities. After measurement, one outcome is found. The atom decayed, or it did not. The detector clicked, or it stayed silent. The photon was recorded here, not there. The wide landscape of possibility has narrowed to a single fact. In standard textbook quantum mechanics, this narrowing is often handled through the projection postulate. The idea is that when a measurement is made, the system is updated into the state corresponding to the result that was observed. If a particle is measured in one location, the wave function is updated to reflect that measured location. If a detector records a certain value, the state is treated as having become the state associated with that value. This rule is useful. It tells physicists how to calculate what happens after a measurement. It allows experiments to be predicted, repeated, and compared. It is part of the machinery that makes quantum mechanics so successful in practice. But it also raises the deeper question of what this update really means. Before measurement, the wave function evolves according to the Schrödinger equation. This evolution is smooth, continuous, and predictable. Given the starting wave function and the right physical conditions, the equation describes how the wave function changes over time. Nothing sudden or selective is supposed to happen. Possibilities shift and spread according to the mathematics. Measurement seems different. Instead of smooth evolution, there is an abrupt update. A range of possible results becomes one actual recorded outcome. The wave function appears to collapse. The theory seems to use one rule for ordinary quantum evolution and another rule for measurement. It is a little like a game that runs perfectly calmly until someone asks for the score, at which point the rulebook quietly changes font and pretends this is completely normal. This is not merely a technical inconvenience. It touches the heart of the question of how reality becomes one thing. If the wave function represents real physical possibility, then collapse looks like a real physical change. If the wave function represents knowledge or information, then collapse may be more like an update in what can be said about the system. Different interpretations of quantum mechanics answer this in different ways. A photon detector makes the issue clearer. A photon may be described by a wave function spread across possible paths or possible points of arrival. The detector records one click in one place. That click is not a vague philosophical mood, it is a physical event. Energy is absorbed. Electrons move. A signal is amplified. Information becomes stored in matter. The result can be copied, displayed, remembered, and checked by others. The same pattern appears again and again. A quantum system with several possible outcomes becomes entangled with a measuring device. The device produces a stable record. The world now contains information that says one result occurred rather than another. The measurement chain has turned a quantum possibility into an ordinary fact, or at least into something that behaves as one. But the measuring device remains the problem. It seems classical because it gives a definite reading, yet it is built from quantum parts. It appears to stand outside the uncertainty it measures, while secretly being made from the same kind of stuff. The detector is not a doorway into another realm of physics. It is matter, interacting with matter. Von Neumann's analysis sharpened the difficulty rather than dissolving it. The boundary between system and apparatus can be moved. The electron can be treated as the system and the detector as the measuring device. Or the electron and detector can be treated together as one larger quantum system with the laboratory outside it. The line can slide outward, from particle to instrument to observer to environment. But sliding the line does not explain why one outcome is experienced. This is why collapse remains such a loaded word. It names something that seems to happen, but its meaning depends on the interpretation being used. For some views, collapse is a real event. For others, it is only an update in information. For others still, there is no true collapse at all, only a larger quantum state developing in ways that make each observer find a definite result. The measurement chain reveals why quantum measurement is not just about tiny particles. It is about the connection between the microscopic event and the macroscopic world of records. The atom decays. The detector clicks. The signal is stored. The result becomes part of reality's paperwork, and reality does love paperwork when it comes in the form of irreversible physical traces. A single click can feel small. Yet, in quantum physics, that click carries a deep question. It marks the place where a mathematical spread of possible outcomes becomes one recorded fact. It asks where the quantum description ends, whether it ever truly ends, and why the world seen afterward contains one result rather than all the possibilities that were allowed before. The measurement chain becomes especially uncomfortable when it is allowed to grow. A quantum event can seem tiny at first. A radioactive atom decays or it does not. A detector clicks or it remains silent. A photon is absorbed in one place rather than another. These are small happenings, tucked away inside laboratory equipment, far from the solid world of tables, doors, chairs, and sleeping cats. But the moment that tiny event is connected to a larger device, and then to a record, and then to the ordinary world, the old question becomes harder to ignore. Where does the uncertainty stop? Erwin Schrödinger pushed this problem into its most famous shape in 1935 with the thought experiment now known as Schrödinger's cat. The example has become so widely repeated that it can sound almost playful, as though quantum physics briefly wandered into a pet shop and caused trouble. But Schrödinger did not invent the scenario as a cute mascot for weird science. He meant it as a serious criticism of applying quantum rules too casually to large everyday objects. The idea begins with a microscopic quantum event. A radioactive atom is placed in a sealed box with a detector. During a certain period of time, the atom may decay, or it may not decay. Quantum mechanics can describe this situation as a superposition of possible outcomes. The decay has happened and has not happened, in the sense that the wave function contains both possibilities until measurement gives a definite result. Now the strange part is connected to something much larger. Inside the box, the detector is linked to a mechanism. If the atom decays, the detector responds, the mechanism is triggered, and the cat is killed. If the atom does not decay, the detector stays quiet, the mechanism does nothing, and the cat remains alive. The fate of the cat becomes tied to the quantum state of the atom. If the quantum description is extended across the whole chain, the atom is in a superposition of decayed and not decayed. The detector is in a superposition of triggered and not triggered. The mechanism is in a superposition of activated and not activated. And the cat appears, at least in the formal description, to be in a superposition of alive and not alive before the box is opened. This is the part that became famous. It is also the part most likely to be misunderstood. Schrödinger was not suggesting that real cats should be placed in boxes for physics. and real cats are not used in quantum measurement experiments of this kind. The point is not animal experimentation with extra mathematics. The point is the boundary between the microscopic world, where superposition is experimentally real, and the macroscopic world, where objects appear definite. A cat is not a photon. A cat is warm, large, noisy, chemically active, breathing, exchanging heat, touching air molecules, and generally being far too complicated to behave like an isolated quantum system. The thought experiment asks what happens when a quantum possibility is amplified into an everyday outcome. If quantum mechanics applies to the atom, and the detector is made of quantum matter, and the mechanism is made of quantum matter, and the cat is made of quantum matter too, then what exactly prevents the whole box from being described as one enormous quantum superposition? The everyday answer is simple enough. The cat is alive, or it is not. There is no familiar experience of opening a box and finding a smooth mixture of both outcomes, which would be deeply inconvenient for everyone involved, especially the cat. Ordinary life gives definite results. The world does not seem to display large objects as visible superpositions of clearly different states, but the deeper physical reason is more subtle. Large objects constantly interact with their surroundings. A cat inside a box would not be an isolated quantum system in the clean laboratory sense. It would be interacting with air molecules, thermal radiation, sound vibrations, chemical processes, internal biological activity, and the walls of the box. Even a speck of dust floating in sunlight is being bombarded by photons and gas molecules. It is continually leaking information into its environment. These interactions matter because quantum superpositions are delicate. For small, carefully isolated systems, scientists can preserve and manipulate superposition. Electrons, photons, atoms, ions, superconducting circuits, and molecules can all show quantum behavior under the right conditions. In controlled experiments, researchers have created superpositions in increasingly large systems compared with single particles. Matter wave interferometry has even shown interference with large molecules made from many atoms, but this is still very different from a living animal in two obvious everyday states. A molecule in an ultra-controlled experiment is not the same as a cat, a chair, or a teapot being both here and there in the visible world. Macroscopic objects are constantly entangled with their environments, and that constant interaction makes delicate quantum alternatives effectively disappear from ordinary experience. This does not mean quantum mechanics switches off when things become large. It means that large objects are extraordinarily difficult to isolate from everything around them. Their quantum behavior is usually hidden by the immense number of interactions taking place every moment. The world looks classical not because it has escaped quantum physics, but because the quantum details become spread, tangled, and practically inaccessible. Schrödinger's cat captures the discomfort in a single image. A microscopic uncertainty is connected to a macroscopic fact. The atom may be described by possible outcomes. The detector converts that possibility into a signal. The mechanism amplifies it. The cat makes the result emotionally and physically impossible to treat as a mere technical detail. That is why the thought experiment remains powerful. It forces the measurement chain out of the laboratory drawer and into the world of ordinary things. It asks whether collapse happens when the atom interacts with the detector, when the detector triggers the mechanism, when the environment records the outcome, or when an observer finally opens the box. It exposes the awkwardness of drawing a clean line between the quantum and the classical. The cat is not there to make quantum physics spooky. The cat is there to make the problem too large to ignore. A tiny event becomes a record. A record becomes a macroscopic state. a macroscopic state becomes part of the familiar world. Somewhere in that widening chain, the many possibilities described by quantum theory stop appearing as many, and one definite reality is found. The box is opened. The result is seen. The world once again seems to have chosen one story. Schrödinger's cat made the measurement problem feel large enough to notice. A tiny radioactive event was connected to a detector, then to a mechanism, then to a living animal, and suddenly the quiet mathematical problem of superposition seemed to have wandered into the room wearing paws. But the thought experiment also helped create one of the most persistent misunderstandings in quantum physics. It made people ask who exactly has to open the box. Does a person need to look inside before reality becomes definite? Does consciousness somehow finish the experiment? Is the universe waiting for a mind to arrive before deciding what happened? The careful answer is no, at least in standard laboratory quantum mechanics. The word observer sounds very human. It suggests a scientist in a white coat leaning over a bench, or a curious person staring at a screen, or someone peering into a box with the serious expression of a person about to become very famous in a physics textbook. But in modern physics, an observer does not usually mean a conscious mind. More often, it means a physical system that becomes correlated with another physical system. It means something has interacted, gained information, and helped create a record. A detector can be an observer in this technical sense. A photographic plate can be an observer. A camera sensor, a computer memory, a cloud chamber, an atom, or the surrounding environment can all play observer-like roles because they can carry information about what happened. They do not need thoughts. They do not need opinions. A detector does not sit there wondering about the meaning of existence before deciding whether to click. It simply interacts according to physical laws. This distinction matters because quantum physics has often been pulled toward a tempting but misleading story. The story says that reality is vague until a human looks at it, and then the human mind somehow forces the universe to choose. It is an appealing idea in a dramatic sort of way. It gives consciousness a starring role. It makes the cosmos feel like it is glancing nervously over its shoulder, waiting to be noticed. But it is not required by the ordinary working machinery of quantum mechanics. A camera can record light in an empty room. A particle can leave a track in a detector long before anyone studies the data. A photon can strike a sensor, release electrons, produce a signal and store information in a device while the scientist is elsewhere, perhaps asleep, perhaps drinking tea, perhaps trying to remember where the charger went. The physical record exists because physical interactions took place, not because a person was present at the exact moment. This does not remove the measurement problem. It makes it cleaner. The real puzzle is not whether human awareness has magic powers. The puzzle is how physical interaction turns quantum possibilities into stable records. When a photon hits a detector, it may transfer energy to electrons in the material. That interaction can be amplified into an electrical signal. The signal can be stored in memory. The memory can later be read, copied, printed, or used in further calculations. At each stage, information about the quantum event spreads into larger and more durable physical systems. Observation in this sense is not awareness, it is correlation. A particle passing through a cloud chamber can leave a visible track because it ionizes atoms along its path. Those atoms help form droplets. The droplets mark where the particle went. The chamber does not understand the track. It does not need to. The track is a physical record, and the record can later be observed by a human. The important measurement-like process has already begun before any conscious interpretation enters the story. Eugene Wigner brought this issue into sharper focus with a thought experiment known as Wigner's friend. In the basic idea, one observer inside a laboratory measures a quantum system and records a definite result. From the friend's point of view, the measurement has produced an outcome. But Wigner, standing outside the sealed laboratory, might in principle describe the entire lab, including the friend, as one large quantum system. This creates a strange tension. Has the outcome become definite for the friend but not yet for Wigner? Can different observers give different quantum descriptions of the same event? Wigner's friend is not mainly about awkward social arrangements in laboratories, although the friendship does seem to involve more sealed rooms than usual. It is about the relationship between observers, records, and quantum descriptions. It asks whether measurement is an absolute event, the same for everyone at once, or whether it depends on how a system is described relative to another system. It pushes the measurement chain one step further and makes the observer part of the system being analysed. Historically, Wigner considered the possibility that consciousness might play a role in collapse, and a few consciousness-based interpretations have appeared in discussions of quantum foundations. But those views are not required for standard quantum theory, and they are not the mainstream explanation for ordinary laboratory outcomes. Most physicists working with quantum systems treat measurement as a physical process involving interaction, information transfer, amplification, and records. That approach fits the way real experiments are performed. In particle physics, detectors register collisions through electrical signals, light flashes, tracks, and deposited energy. In quantum optics, photon detectors record individual absorption events. In quantum computing, qubits are measured by coupling their fragile quantum states to larger systems that produce classical information. A human may eventually read the result, but the human is not the first link in the chain. The serious measurement problem remains profound enough without turning it into a story about the universe needing attention. The difficulty is that quantum theory describes possible outcomes, while the world of records contains actual outcomes. A measurement does not have to be a conscious gaze. It can be a physical interaction that makes information about an event available, stable, and difficult to erase. Schrödinger's cat asks where the boundary lies between quantum uncertainty and everyday definiteness. The observer question asks whether that boundary depends on a person looking. The safer scientific answer is that the boundary is not created by eyesight or awareness alone. It is tied to physical processes that copy, store, and spread information. Reality does not appear to wait politely for a human mind before doing anything. The moon does not need an audience. A detector does not need admiration. A photon does not pause at the edge of a sensor, wondering whether anyone is emotionally prepared for the result. The universe is stranger than that, but also more disciplined. Measurement is not simply looking, it is interaction becoming record. It is a quantum possibility leaving a trace in matter. It is the moment when information stops being private to a tiny system and begins to spread into the wider world, where one outcome can be found, checked, remembered, and treated as real. The observer does not have to be a person. A detector can record, a camera can store, a cloud chamber can leave a track. The surrounding world itself can become involved, not by thinking about a quantum system, but by physically interacting with it. This is where decoherence becomes one of the most important ideas in modern discussions of quantum measurement. Quantum decoherence is the process by which a quantum system loses visible interference between its possible alternatives because it becomes entangled with its environment. The word sounds technical, and it is, but the basic idea can be approached gently. A quantum system may begin in a delicate superposition, with different possibilities still able to overlap and interfere. But when that system interacts with surrounding air molecules, stray photons, heat, dust, laboratory equipment, or almost anything else, information about those alternatives can leak outward into the environment. Once that happens, the alternatives can no longer interfere in the same visible way. It is a little like a quiet ripple pattern on a still pond. If the water is calm, the ripples can spread, overlap, and form clear patterns. But if rain begins to fall, wind brushes the surface, leaves drop in, and small disturbances arrive from every direction, the original pattern becomes practically impossible to follow. The ripple has not been denied by philosophy. It has been physically buried beneath a wider tangle of interactions. Quantum decoherence is not literally pond water, of course, but the comparison helps capture the loss of delicate structure through contact with a larger environment. One of the key early figures in this subject was Heinz-Dieter Zeh. In the 1970s, Zeh argued that the interaction between a quantum system and its environment could explain why quantum superpositions become effectively invisible at everyday scales. Later, Wojciech Zurek became one of the major scientists who developed the modern understanding of environment-induced decoherence, showing how the environment plays an active role in the emergence of classical-looking reality. This is an important shift. Instead of treating measurement as a mysterious human act, decoherence treats it as part of a wider physical process. A quantum system does not need a conscious observer in order to lose visible interference. It only needs to become entangled with something around it. A speck of dust floating in sunlight is not isolated. Photons from the sun strike it and scatter away. Air molecules bump into it. Thermal radiation passes to and from it. Each interaction can carry away tiny amounts of information about the dust grain's position. The dust grain is therefore constantly becoming linked to its surroundings. Its possible alternatives are not preserved in a clean, private quantum state. They are being spread into the environment almost instantly. This helps explain why everyday objects look stable and definite. A chair does not appear to sit in a delicate superposition of several positions because it is constantly interacting with the world around it. Light bounces from it, air touches it, heat flows through it, sound waves, vibrations, and countless microscopic contacts continually connect it to its surroundings. For a large warm object, decoherence can happen with astonishing speed, often on timescales so tiny that they are effectively impossible to notice in ordinary experience. That is why the world looks classical. The quantum phase relationships that allow interference are still part of the deeper theory, but they become inaccessible in practice. The alternatives have not remained neatly available to recombine and produce a visible interference pattern. They have become entangled with too many environmental details. To recover the original interference, one would have to control not only the object, but also the vast number of particles and fields that have interacted with it. For an ordinary object in an ordinary room, that is not just difficult, it is absurdly beyond practical reach. This is why laboratories that study quantum effects work so hard to isolate systems. Photons, electrons, ions, atoms, superconducting circuits. And ultra-cold gases must often be protected from environmental noise. They may be cooled, shielded, placed in vacuum chambers, or carefully separated from outside disturbances. The aim is to preserve quantum coherence long enough for superposition and interference to be observed or used. Quantum computers face this challenge constantly. Their quantum bits must maintain delicate relationships while the surrounding world does its usual enthusiastic job of interfering. Decoherence, therefore, gives a powerful answer to part of the measurement problem. It explains why the interference between alternatives disappears when quantum systems interact with their environments. It explains why detectors, measuring devices, and everyday objects do not show obvious superpositions. It explains why the world of tables, clocks, screens, and laboratory readings appears definite, even though everything is ultimately built from quantum matter, but it does not solve every part of the problem on its own. Decoherence explains why alternatives stop interfering in any visible or usable way. It explains why a system begins to behave as though one classical outcome has emerged. But in many interpretations, decoherence by itself does not explain why one particular outcome is experienced rather than another. It turns a sharp quantum superposition into something that looks like a set of effectively separate possibilities, each tied to different environmental records. But whether that means one outcome truly collapses, or many outcomes continue in separate branches, or something deeper was always definite, depends on the interpretation of quantum mechanics being used. So decoherence is not a magic eraser, it is a physical process. That distinction matters. It does not say that possibilities vanish because someone becomes aware of them. It says that fragile quantum relationships are dispersed into the surrounding world through ordinary physical contact. It does not need drama, it needs interaction. And the universe is extremely good at interaction. The observer question made clear that measurement is not simply human awareness. Decoherence goes further by showing how the environment itself can behave like an enormous recording system. Every scattered photon, every disturbed molecule, every transferred bit of heat can help carry information away from a quantum system. The result is a world where delicate superpositions become hidden, and stable records begin to dominate experience. Possibility does not disappear because the universe has been caught misbehaving. It disappears from view because the wider world has touched it. Decoherence explains how delicate quantum interference becomes hidden when a system interacts with its environment. But there is another question waiting just behind it. If the environment is constantly touching quantum systems, scattering light, absorbing heat, carrying away traces, and spreading information outward, could that same environment be doing more than simply making quantum weirdness disappear from view? This is the idea behind quantum Darwinism. Quantum Darwinism is a proposal developed by Wojciech Zurek, whose work at Los Alamos National Laboratory has been central to modern thinking about decoherence and the emergence of the classical world. The name sounds as if atoms have started growing beaks and competing for islands, which would be a very different documentary. But the idea is more precise than the name suggests. It proposes that the environment not only destroys visible interference between quantum alternatives, but also selects and spreads information about certain stable states. Those stable states are called pointer states. A pointer state is a state of a system that can survive interaction with the environment well enough to leave reliable copies of information around it. The name comes from the image of a measuring instrument, with a pointer that settles into one definite position. In a real experiment, the pointer might be a needle, a digital readout, a detector signal, or any stable physical record. The deeper idea is that not every quantum state survives environmental contact equally well. Some states are fragile, others are robust. The robust ones are the states that the environment can copy, preserve, and make available to many observers. This helps explain why the world looks shared. Ordinary experience depends on indirect information far more than it may seem. When a person sees a chair, they are not usually touching the chair with their eyes, which is just as well, because that would make furniture shopping much worse. They are detecting light that has bounced off the chair. Photons scatter from its surface, travel across the room, enter the eye, and trigger signals in the retina. The same is true for a tree, a book, a measuring needle, or a mug sitting on a table. Most visible objects are known through environmental fragments, especially light. This means the environment is not merely background scenery. It acts like a vast carrier of records. Photons bouncing from a chair carry information about the chair's position, shape, colour and surface. Air molecules can carry information through collisions. Thermal radiation can carry information about temperature and structure. Sound waves can carry information about movement and vibration. The world is full of traces, and ordinary observers are constantly sampling them. Quantum Darwinism says that objectivity may arise because many copies of certain information are spread through the environment. If several people look at the same chair from different parts of a room, they can agree that the chair is there because they are each intercepting different photons that carry broadly consistent information about it. No one has to disturb the chair in some dramatic way. The information has already been copied outward many times. This is called redundancy. A fact becomes objective-looking when many separate fragments of the environment contain the same basic information. One observer can collect a tiny fraction of the scattered light and infer the chair's position. Another observer can collect a different fraction and reach the same conclusion. The agreement does not require direct access to the entire quantum state of the chair. It depends on many environmental records pointing toward the same stable outcome. In this view, the environment behaves a little like a messenger that is impossible to stop talking. It does not merely erase the delicate interference between alternatives. It also broadcasts selected information about stable states. The states that survive this process become the ones that many observers can find, compare, and treat as ordinary reality. The world looks definite partly because the same information has been copied so widely that it becomes very hard to avoid. This connects naturally to measurement. A measuring device produces a stable record, but that record does not remain sealed away in a private corner of existence. Light reflects from the display. Electrical signals move through circuits. Heat is released. The result becomes entangled with the surrounding environment. Information about the measurement spreads outward. Other systems can, in principle, access it. The record becomes part of the shared world. Quantum Darwinism does not say that the environment is conscious or that it deliberately chooses outcomes. There is no tiny committee of photons voting on whether a measuring needle should point left or right. The selection is physical, not intentional. Certain states are simply more stable under environmental interaction, and those states are more likely to leave redundant records. The process is Darwinian only in the broad sense that some states survive and spread information better than others. This idea helps explain why classical reality appears objective. A measurement result seems real not just because one detector has registered it, but because the result can be copied into many physical systems. It can be seen, stored, repeated, written down, photographed, remembered, and checked. The world becomes dependable because stable records can be shared. Still, quantum Darwinism does not remove every deep question. It helps explain how the appearance of objective classical reality emerges from quantum systems interacting with their environments. It strengthens the role of decoherence by showing how the environment can both suppress interference and spread information. But it does not, by itself, settle every interpretation of quantum measurement. Different views of quantum mechanics can still disagree about whether only one outcome truly exists, whether many branches persist, or whether something deeper determines what is found. Even so, it changes the feeling of the measurement problem. The environment is no longer just the thing that ruins delicate quantum experiments, like an over-enthusiastic guest knocking over a carefully arranged tray. It is also part of how the familiar world forms. It carries records. It preserves stable information. It allows many observers to agree on the same facts without needing direct access to the hidden quantum machinery underneath. Possibility fades from view through decoherence, but the shared world appears through records. The light in a room, the air around an object, the heat it gives off, and the signals stored in a detector all help turn a private quantum event into public reality. The world seems definite because the environment is always whispering the same answers in many different places. Decoherence and quantum Darwinism offer a way to understand why the world looks classical, shared and stable. They show how the environment can hide interference between quantum possibilities and spread many copies of information about robust states. A chair looks like a chair because photons, air molecules, thermal radiation, and countless other environmental traces all help carry consistent information about it. But there is still a deeper question underneath. Does reality truly choose one outcome, or does it only appear that way from inside one part of a much larger quantum story? Hugh Everett offered one of the boldest answers in the 1950s. His proposal is now commonly known as the many worlds interpretation, although Everett's original language focused more carefully on the universal wave function and relative states. The phrase many worlds became more widely known later, especially through the work of Bryce DeWitt, who helped popularize the interpretation and gave it the memorable name that still follows it around, rather like a dramatic hat it cannot quite remove. Everett's central move was simple to state, though not simple to accept. He removed wave function collapse from the foundations of quantum mechanics. In standard textbook language, measurement is often described as a special event. Before measurement, the wave function contains several possible outcomes. After measurement, the wave function collapses into the outcome that is actually observed. The electron is found here, the detector clicks there, the atom has decayed, or it has not. The possible becomes definite. Everett asked what would happen if that special collapse never occurred. In the many worlds view, the wave function always evolves smoothly according to the Schrödinger equation. There is no sudden break in the process when a measurement happens. There is no extra rule that steps in and says, this possibility survives, and the others must leave quietly through the side door. Instead, all the possibilities contained in the wave function continue as parts of the universal quantum state. Measurement, in this picture, is not a magical selection. It is a branching of effective histories. Imagine a quantum system that can produce two possible measurement results. A detector interacts with it. One version of the detector records one result, and another version records the other result. An observer becomes correlated with one recorded outcome in one branch, and with the other recorded outcome in another branch. From inside each branch, the result appears definite. The observer sees one outcome, remembers one outcome, and inhabits one consistent history. The key point is that each observer within each branch experiences a single result. No one feels themselves split like a badly handled biscuit. No one sees all outcomes layered on top of one another in ordinary perception. Each branch contains a version of events that looks classical, stable, and definite from the inside. This is how many worlds answers the title. Reality becomes one thing for each observer inside each branch, but at the deepest level, the universal wave function has not chosen only one outcome. The apparent single result is local to a branch of the broader quantum state. This can sound extravagant. It is easy to hear many worlds and imagine it means every possible fantasy exists somewhere. A universe where socks rule parliament. A universe where the moon is made of soup. a universe where someone finally understands printer settings on the first attempt. But that is not what the interpretation says. Many worlds is not the claim that every imaginable story becomes real. It is tied specifically to the mathematical possibilities contained in the quantum wave function and the way quantum systems become correlated through measurement. The branches are not created by wishes, stories, or idle thoughts. They arise from quantum interactions described by the theory. A measurement links a system, an apparatus, an observer, and the environment. The different possible outcomes become entangled with different records. Each branch contains a consistent pattern of correlations. Decoherence is crucial here. Without decoherence, many worlds would struggle to explain why branches do not visibly interfere with one another in everyday experience. Decoherence shows how environmental interaction causes different alternatives to lose the ability to produce observable interference. The branches become effectively separate, not because a cosmic knife has cut them apart in some theatrical way, but because the information has spread into too many environmental degrees of freedom. The alternatives no longer recombine in any ordinary practical sense. This is why many worlds connect naturally to quantum Darwinism. The environment helps create stable records within each branch. Photons, air molecules, detector signals, and memory states all become correlated with one outcome rather than another. Each branch contains its own network of records, and those records agree with one another. The observer inside a branch finds a definite world because every accessible trace points to that same outcome. In this view, collapse is not a physical event. It is an appearance produced from the perspective of an observer who is now part of one branch. The observer sees one result because they have become correlated with that result. The other possible outcomes are not destroyed. They continue in other branches, inaccessible in practice, because decoherence has separated the histories so thoroughly. This interpretation has an unusual kind of simplicity. It keeps the Schrödinger equation as the single smooth rule for quantum evolution. It avoids adding a special collapse process whose timing and physical nature are difficult to define. It treats measuring devices, observers, laboratories, and particles as all part of the same quantum universe. The cost is enormous in another way. Many worlds asks the listener to accept that the universal wave function contains a vast branching structure of outcomes, each experienced as definite by observers within it. Some physicists find that elegant, others find it excessive. Some see it as the cleanest reading of the mathematics. Others feel it multiplies reality beyond what can be directly confirmed. This is why many worlds remains an interpretation, not an experimentally settled fact. It makes the same ordinary predictions as standard quantum mechanics in the situations where the theory has been tested. Its appeal is not that it predicts a simple new laboratory result, but that it offers a different way to understand what the existing mathematics means. The measurement problem, then, has not vanished. It has changed shape. Instead of asking why the wave function collapses, many worlds asks why observers experience one branch as their reality, and how probability should be understood if all outcomes occur in some branch. The theory removes one mystery and reveals another. This is quite normal in foundations of physics, where solving a problem often means persuading it to sit in a different chair. Many worlds refuses to let reality choose only one outcome at the deepest level. It says the universal wave function keeps everything that quantum mechanics allows, evolving smoothly without collapse. Yet inside any one branch, reality still feels singular. A detector gives one reading, a scientist records one result, a memory contains one history. The world becomes one thing from within, even if the deeper theory may contain more than one way for the story to continue. Many worlds gives one answer to the measurement problem by refusing to collapse the wave function. It says that the universal quantum state keeps evolving smoothly, while each observer finds a definite result from within one branch of that larger structure. It is an elegant idea to some physicists, and a rather expensive way of keeping the mathematics tidy to others. There is another route. Instead of saying that all possible outcomes continue in different branches, hidden variable theories ask whether quantum probability might be sitting on top of a deeper level of reality. Perhaps the wave function does not tell the whole story. Perhaps particles really do have definite properties, even when standard quantum mechanics does not describe them in that familiar classical way. Perhaps the uncertainty is not because nature is undecided, but because there are deeper details hidden from the usual formulation of the theory. This does not mean hiding variables in the suspicious sense, like reality has put them in a drawer and is refusing to tidy up. A hidden variable is simply an extra element of physical description not included in standard quantum mechanics. The hope is to restore a clearer kind of definiteness beneath the probabilities without losing the extraordinary predictive success of quantum theory. Louis de Broglie explored one version of this idea in the 1920s. He had already proposed that matter could have wave-like properties, and he also developed an early pilot wave picture. In this approach, a particle is not merely replaced by a wave function spread through possibility. It has a definite position, while a real wave-like structure guides its motion. David Bohm revived and developed this idea in 1952, creating what is now often called Bohmian mechanics, or pilot wave theory. In Bohm's version, particles always have definite positions. They do not wait for measurement to become located somewhere. They are already somewhere. But their motion is guided by the wave function, which evolves according to the usual quantum rules and shapes the path the particles take. This gives measurement a very different meaning. In standard textbook quantum mechanics, measurement can seem to produce one result from a spread of possible outcomes. In Bohmian mechanics, the particle already has a definite position before measurement, and the act of measuring reveals or amplifies that definite configuration through interaction with the measuring device. The wave function still matters deeply because it guides the particle, but reality is not randomly choosing from nothing at the moment of measurement. The particle's actual position and the guiding wave together determine what happens. The double-slit experiment looks different through this lens. An electron has a definite path, but the pilot wave passes through the experimental arrangement and guides the electron in a way that produces the interference pattern across many trials. Each electron arrives at one point on the screen, as usual, but the overall pattern reflects the influence of the wave. In this view, the particle is always one thing in position, even while the guiding wave carries information about the full arrangement. This is one reason pilot wave theory is appealing. It preserves a kind of underlying realism. The electron is not merely a set of probabilities waiting for a detector. It has a real position. The universe has definite particle configurations. Measurement does not summon facts into existence from pure uncertainty. It reveals facts shaped by a deeper quantum guidance. But there is a cost, and it is not a small one. John Bell changed the discussion of hidden variables in 1964 with Bell's theorem. Bell showed that no theory based on local hidden variables could reproduce all the predictions of quantum mechanics. Local, in this context, means that influences cannot travel instantly between distant objects, and that what happens here should not depend immediately on what measurement is chosen far away. Hidden variables, in this context, mean deeper definite properties that would explain the outcomes beneath the quantum probabilities. Bell's theorem was powerful because it turned a philosophical dispute into something experimentally testable. If the world worked through local hidden variables, then certain statistical patterns should obey limits now known as Bell inequalities. Quantum mechanics predicted that those limits could be violated in experiments involving entangled particles. Later Bell test experiments confirmed the quantum predictions again and again. The work of physicists such as John Clauser, Alain Aspect, and Anton Zeilinger helped show that nature does not behave according to simple local hidden variable expectations. This does not rule out every possible theory with deeper variables. It rules out a broad and important class of local hidden variable theories. Bohmian mechanics survives because it is explicitly non-local. In pilot wave theory, the behavior of one particle can depend on the configuration of other particles in a way that does not fit the old classical demand for strictly local causes. That can sound alarming, so it needs to be handled carefully. Non-locality in this context does not mean a useful faster-than-light messaging system. It does not let someone send tomorrow's lottery numbers across the galaxy, which remains disappointing but probably wise. It means that the deeper structure required to reproduce quantum predictions cannot be understood as a simple collection of local properties evolving independently in separate places. This is where hidden variable theories become both attractive and uncomfortable. They can restore definiteness, but not the old classical world exactly as it was. The particle may have a real position, yet the guiding wave connects the system in a deeply non-classical way. Reality can be one thing, but not in the simple clockwork style imagined before quantum theory. Pilot wave theory therefore gives one possible answer to the title. Reality becomes one thing because, at the level of particle positions, it was already one thing. The measurement does not select an outcome from a purely open menu. It reveals the actual configuration that has been guided by the wavefunction all along. The probabilities arise because observers do not know the exact hidden configuration of the system, even though the deeper motion is deterministic. Many worlds avoids collapse by allowing all outcomes to continue in different branches. Bohmian mechanics avoids collapse by keeping particles definite and allowing the wave function to guide them. Both take the mathematics of quantum mechanics seriously. Both try to remove the mysterious special status of measurement. But they pay for that clarity in different ways. Many worlds accepts a vast branching quantum state. Pilot wave theory accepts definite particles guided by a non-local wave. Neither approach returns physics to the old comfort of classical certainty. Quantum theory does not let that door reopen so easily. But pilot wave theory shows that the measurement problem can be approached without saying that reality waits undecided until the detector clicks. Perhaps the particle was always somewhere. Perhaps the guiding wave carried the structure of possibility. Perhaps measurement is not the birth of a fact, but the moment a hidden fact becomes part of the visible record. The world becomes one thing because, underneath the probabilities, it may never have stopped being one. Pilot wave theory gives reality a hidden definiteness. Particles have actual positions. A guiding wave shapes their motion. Measurement does not have to summon one result from nothing, because underneath the ordinary quantum description, the world is already arranged one way rather than another. Objective collapse theories take a different path. Instead of saying that particles always had definite hidden positions, objective collapse theories suggest that wavefunction collapse is a real physical process, not just a change in knowledge, not just a convenient update after a detector clicks, not merely a rule in a textbook that tells physicists what to calculate next. Collapse, in this view, is something nature actually does. The idea is simple in spirit, though technically difficult. A quantum system can exist in a superposition of possible states, but under certain conditions, that superposition physically reduces to one outcome. reality becomes one thing because the wave function really collapses. The possibilities do not continue forever as separate branches, and they are not only hiding a deeper definite particle arrangement, they are physically narrowed by a genuine process built into nature. One of the most important objective collapse models was proposed by Giancarlo Girardi, Alberto Rimini, and Tullio Weber in the 1980s. Their Girardi-Rimini-Weber theory suggested that quantum systems undergo rare spontaneous collapses. For a single microscopic particle, such a collapse would be extremely unlikely over ordinary timescales, meaning that small quantum systems could still show familiar quantum behavior, such as superposition and interference. But for large objects made of enormous numbers of particles, the effect would become overwhelmingly important. This is the clever part. A single particle may remain quantum and delicate. A large object, made from countless particles, would collapse into a definite state extremely quickly because there are so many opportunities for one of its parts to undergo collapse. In this kind of theory, a dust grain, a measuring needle, a table, or a cat does not need a conscious observer to become definite. Large objects become definite because the modified laws of physics make sustained macroscopic superpositions incredibly unstable. That gives objective collapse theories a very direct answer to the measurement problem. The measuring device produces one result because physical collapse happens. The pointer points one way. The detector records one click. The screen shows one mark. The world becomes definite not because a person looks, and not because the environment merely hides interference, but because superposition itself is physically reduced. This is different from ordinary textbook collapse. In standard quantum mechanics, collapse is often introduced as a rule for updating the state after measurement. It works for calculation, but it does not clearly say whether collapse is a real event, a change in information, or a convenient shortcut. Objective collapse theories try to remove that ambiguity. They say collapse is real, and they alter the quantum rules slightly to make it happen. Roger Penrose has proposed a different kind of objective collapse idea, connected to gravity. Penrose has suggested that superpositions involving significantly different space-time geometries may be unstable, and that gravity could play a role in causing collapse. This idea is speculative. It is not established consensus, and it has not replaced standard quantum mechanics. But it is scientifically interesting because it links the measurement problem to one of the deepest unresolved issues in physics: the relationship between quantum theory and gravity. This matters because gravity is not just another laboratory detail. General relativity describes gravity as the curvature of space-time, while quantum mechanics describes matter and energy through wave functions, probabilities, and measurement outcomes. These two frameworks are both extremely successful in their own domains, but they are not yet unified into a complete theory of quantum gravity. Penrose's proposal sits near that boundary, where the shape of space-time and the fate of quantum superpositions may be connected. Objective collapse models have one major advantage over many interpretations of quantum mechanics. In principle, they can be tested. If collapse is a real physical process that changes the standard quantum rules, then it may leave tiny traces. It may cause small deviations from ordinary quantum predictions under carefully controlled conditions. It may produce faint heating, tiny losses of interference, or limits on how large and complex a quantum superposition can become. This makes objective collapse especially appealing to researchers who want the measurement problem to become experimentally sharper. Instead of only asking what the mathematics means, scientists can ask whether nature shows any sign of collapse beyond standard quantum theory. Matter wave interferometry, optomechanics, and precision measurement are all relevant here. These fields try to prepare larger and larger systems in quantum states, control their interactions with the environment, and look for any boundary where ordinary quantum behavior begins to fail. Matter wave interferometry tests whether increasingly massive particles or molecules can still show interference. Optomechanics studies tiny mechanical systems whose motion can approach the quantum regime, sometimes using light to cool, control, and measure them. Precision measurement searches for extremely small effects that could reveal new physics. These experiments are difficult because ordinary decoherence is already a powerful enemy. Air molecules, thermal radiation, vibrations, and stray electromagnetic noise can destroy visible interference without needing any new collapse process at all. The challenge is to separate ordinary environmental decoherence from a possible fundamental collapse. So far, standard quantum mechanics remains extraordinarily successful. Objective collapse theories remain possible in some forms, constrained by experiments, but not confirmed as the correct answer. They are serious proposals, not decorative mysteries, but they are not established facts. Their importance is conceptual as much as experimental. They show that reality could become one thing, because nature contains a built-in mechanism that makes it become one thing. In many worlds, collapse is refused. In pilot wave theory, definiteness hides beneath the wave function. In objective collapse, the wave function itself is physically reduced. The result is a universe that does not wait for consciousness, does not need a special classical measuring device, and does not require every outcome to persist in a branching structure. Possibilities can be real for a while, but not forever. Under the right conditions, nature narrows them. Reality chooses for itself, quietly, physically, and perhaps with no observer required. Objective collapse theories try to make measurement into a real physical process. They ask whether nature itself might contain a mechanism that turns quantum possibilities into definite outcomes. But in modern laboratories, measurement is not only a question about interpretation, it is also a practical craft, repeated every day with extraordinary precision. A quantum experiment does not usually look like a philosopher standing in a dark room asking reality to explain itself. It looks more like cooled equipment: vacuum chambers, lasers, detectors, electronics, careful shielding, and a great deal of patience. Often there is also a cable somewhere causing trouble, because even at the foundations of reality, cables retain their ancient right to be irritating. Modern physicists treat measurement as a physical process. A quantum system is prepared in a particular state. It is allowed to evolve, interact, interfere, entangle, or respond to a controlled field. Then it is coupled to a measuring device. The measurement produces information, and that information becomes a record. A detector clicks, a current changes, a pulse of light is collected, a computer stores a result. The mystery of measurement is still deep, but in the laboratory it is handled with careful machinery and repeatable procedures. This is especially clear in experiments on quantum foundations. Alain Aspect, John Clauser, and Anton Zeilinger are closely associated with Bell test experiments and the study of quantum entanglement. Their work helped show that the correlations predicted by quantum mechanics cannot be explained by simple local hidden variable theories. The focus here is not entanglement as a whole, but what those experiments reveal about measurement. Two particles can be prepared in a shared quantum state, measured far apart, and still show statistical correlations that match quantum theory rather than classical expectations. The measurements themselves are not casual observations. They require precise choices of detector settings, careful timing, controlled photon sources or particle pairs, and rigorous statistical analysis. Each individual result may look simple. One detector records one outcome, another detector records another. But when many trials are collected, the pattern reveals something profound about how quantum systems behave when measured. This is a recurring theme in quantum physics. One measurement rarely tells the whole story. A single detected photon does not reveal an entire wave function. A single qubit readout does not uncover every detail of a quantum state. A single atom measured once gives one outcome, not the full probability landscape. To understand the underlying state, researchers must repeat experiments many times under controlled conditions and build up the statistics. Quantum state tomography is one method for doing this. It is a technique used to reconstruct the state of a quantum system from many repeated measurements performed in different ways. The word tomography is also used in medical imaging, where many slices of information can be combined into a fuller picture. In quantum physics, the idea is similar in spirit, though the object being reconstructed is not a body or a bone, but a mathematical description of a quantum state. Many measurements are needed because each individual measurement gives only a limited piece of information. This is why quantum prediction can feel strange but still be reliable. Individual outcomes may be unpredictable. A detector may click here rather than there. A qubit may be found in one measured state rather than another. But across many repeated trials, the statistical pattern can be predicted with remarkable accuracy. Quantum mechanics does not promise that every single event will be known in advance. It promises that the distribution of many events will follow precise rules. In quantum computing, measurement is part of the machine itself. Superconducting qubits, used by research groups and companies around the world, are tiny electrical circuits cooled to extremely low temperatures so that quantum states can be controlled. They can be placed into superpositions, entangled with other qubits, manipulated by microwave pulses, and finally measured by coupling them to larger electrical signals. The delicate quantum state is converted into classical information that can be stored and read. Trapped ions offer another controlled platform. Individual atoms are held using electromagnetic fields and manipulated with lasers. Their quantum states can be prepared with great care, allowed to interact, and then measured through the light they emit. The National Institute of Standards and Technology has played a major role in this field, especially in precision measurement, atomic clocks, trapped ions, and quantum information research. These experiments show how measurement can be both deeply foundational and intensely practical. Photons are also central to modern quantum experiments. In quantum optics, scientists prepare single photons, send them through interferometers, entangle them, separate them, and detect them with sensitive photon counters. The University of Vienna has been strongly associated with important work in quantum foundations and quantum information, including experiments connected to Anton Zeilinger and his collaborators. In these settings, measurement often means turning a tiny quantum event into a macroscopic signal, one that can be counted, timed, and compared with theory. Ultracold atoms provide another route into controlled quantum behavior. At temperatures close to absolute zero, atoms move slowly enough for their quantum properties to become easier to study collectively. Researchers can create quantum gases, optical lattices, and highly controlled many-body systems. Measurement may involve imaging the atoms with light, tracking their distributions, or reading out correlations after carefully prepared interactions. These systems allow physicists to explore how quantum behavior emerges, spreads, and becomes visible at larger scales. At CERN, the European Organisation for Nuclear Research, measurement takes on a different scale. Particle detectors surrounding collision points do not simply watch particles in the ordinary sense. They record tracks, energies, decay products, flashes of light, electrical signals, and timing information. A collision inside a detector may produce a storm of particles, most of which exist for tiny fractions of a second. The detector turns those brief events into data that can be analysed afterward. Once again, quantum events become stable records through physical interaction. Across all these settings, measurement is not an afterthought. It is where theory meets the world. A quantum state may be prepared beautifully, but the experiment only becomes evidence when outcomes are recorded. The detector, the environment, the electronics, the statistics, and the stored data all matter. They are part of the bridge between the wave function and the facts scientists can compare. This brings the discussion back from objective collapse to the working laboratory. Whether collapse is real, apparent, avoided, hidden, or replaced by branching depends on interpretation. But the physical act of measurement remains unavoidable. Quantum systems must be coupled to larger systems. Information must be amplified. Records must become stable enough to survive. The philosophical puzzle is still there, quietly humming beneath the equipment. Yet modern experiments show that quantum measurement is not a vague mystery floating above science. It is a precise physical practice involving detectors, entanglement, environmental interaction, repeated trials, and recorded information. Reality becomes one thing in the laboratory, one result at a time, then becomes science when those results gather into a pattern. The question at the centre of quantum measurement is not whether the world is real. The world is very good at being real. Tables hold up cups. Floors remain stubbornly beneath feet. A laboratory detector either records a signal or does not. A screen shows one mark in one place. A notebook contains one result, not a polite selection of alternative endings. The deeper question is how that definite world arises from a theory built around possible outcomes. Quantum measurement is the process through which a spread of possibilities becomes a record that can be seen, shared, stored, checked, and remembered. Before measurement, a quantum system may be described by a wave function, a mathematical object that gives probabilities for what may be found. After measurement, the world contains one result. The detector clicked here, the photon arrived there, the atom decayed, or it did not. Possibility has become fact, at least in the world of accessible records. That is why measurement sits so close to the title. Reality becomes one thing not because everything before measurement is imaginary, and not because a human mind reaches out and commands the universe to make a decision. It becomes one thing because quantum systems interact with measuring devices, environments, records, and observers in ways that make one outcome available within ordinary experience. The route to this puzzle began with classical certainty. Isaac Newton gave physics a world of definite positions, definite speeds, forces, paths, and predictable motion. Pierre-Simon Laplace sharpened that picture into the idea that, with perfect knowledge, the future and past could be calculated in principle. James Clerk Maxwell brought electricity, magnetism, and light into a continuous classical framework. Measurement seemed simple. A ruler, clock, telescope, or thermometer revealed a property that already existed. Then the small world began refusing to behave. Max Planck showed that black body radiation could be explained if energy exchange occurred in discrete packets. Albert Einstein treated light as individual quanta to explain the photoelectric effect in 1905. Niels Bohr used fixed energy levels to explain the sharp spectral lines of hydrogen. Erwin Schrödinger gave quantum waves a mathematical form. Max Born showed that the wave function should be used to calculate probabilities. Werner Heisenberg introduced the uncertainty principle, making clear that some pairs of properties cannot both be made perfectly definite in the quantum description. Step by step, physics learned that the old classical picture was not wrong at human scales, but incomplete atoms, photons, electrons, radiation, and measurement events did not always fit the idea of hidden classical facts waiting to be uncovered. John von Neumann made the measurement problem more formal by analysing the measurement chain. A quantum system interacts with an apparatus. The apparatus produces a signal. The signal becomes a record. The record may eventually be read by a person. But the apparatus itself is made of quantum matter. Its parts are atoms, electrons, fields, and interactions. If quantum mechanics applies to everything physical, then the measuring device cannot simply sit outside the theory like a referee with special privileges and a clipboard. This is where different interpretations separate. In collapse views, the wave function genuinely or effectively reduces to one outcome when measurement occurs. Objective collapse theories, such as the Gherardi-Rimini-Weber theory, developed by Giancarlo Gherardi, Alberto Rimini, and Tullio Weber, take this further by suggesting that collapse is a real physical process. In that picture, large systems naturally become definite because the quantum rules include a mechanism that suppresses large-scale superpositions. Roger Penrose has suggested, speculatively, that gravity may play a role in collapse, although that remains far from established consensus. In the many worlds interpretation proposed by Hugh Everett and later popularised under that name by Bryce DeWitt, collapse does not happen at all. The universal wave function keeps evolving smoothly. Measurement links each possible outcome to different records, observers, and environments. Each branch contains one definite experience from the inside, even though the deeper quantum state contains many effective histories. Reality becomes one thing locally, within a branch, rather than globally, at the deepest level. Bohmian mechanics, developed from Louis de Broglie's pilot wave idea and later by David Bohm, offers another answer. Particles have definite positions all along, guided by a real wave-like structure. Measurement does not force reality to choose from nothing. It reveals a definite configuration shaped by the guiding wave. John Bell's theorem later showed that simple local hidden variable theories cannot reproduce all quantum predictions, but Bohmian mechanics survives by accepting a non-local structure that does not fit the old classical picture. Across these interpretations, the same experimental facts remain. Quantum mechanics predicts measurement outcomes with extraordinary accuracy. It explains atoms, lasers, semiconductors, magnetic resonance, superconducting circuits, trapped ions, photon experiments, and the statistical patterns seen in precision laboratories. The disagreement is not over whether the theory works. It works almost suspiciously well, like a quiet machine in the corner that refuses to explain why it is so good at its job. The disagreement is over what the success means. The measurement problem is not evidence that reality is fake. It is not proof that consciousness controls matter. It is not a license to replace physics with wishful thinking wearing a lab coat. It is a serious scientific and philosophical question about how probabilities, physical interactions, information, records, and definite outcomes fit into one coherent picture. Decoherence explains a large part of why the everyday world looks stable. H. Dieter Zeh and Wojciech Zurich helped show how interaction with the environment causes quantum alternatives to lose visible interference. Air molecules, photons, heat, dust, and surrounding matter constantly carry information away from systems. For large warm objects, delicate quantum relationships become inaccessible extremely quickly. Quantum Darwinism, also developed by Zurich, goes further by suggesting that the environment spreads many copies of information about stable pointer states. Light bouncing from a chair, a tree, or a measuring needle carries repeated information into the surrounding world. Many observers can agree on the same fact because they are sampling different fragments of the same environmental record. This is why ordinary reality feels so settled. The world is not just one private measurement. It is a vast web of physical correlations. Results are copied into detectors, screens, memories, light, air, heat, and matter. Quantum alternatives become hidden from practical access, while stable records become widely available. Reality may become one thing not through drama, magic, or a cosmic decision made under pressure, but through interaction. A quantum system touches a detector. The detector touches its environment. Information spreads. Records stabilize. The world gathers around one accessible outcome. Possibility becomes fact when it leaves enough traces to be part of the shared world. Quantum measurement is the reason the mathematical possibilities of quantum theory become the single recorded outcomes that make up ordinary experience. That sentence sounds calm enough, but it carries one of the deepest puzzles in modern science. Before measurement, a quantum system may be described by a wave function, a mathematical structure that gives probabilities for what might be found. After measurement, the world contains a result. A detector has clicked. A screen has shown a mark. A laboratory notebook contains one recorded value. The wide, delicate landscape of possibility has become a fact that can be shared, checked, remembered, and built into the next experiment. This is why the question of why reality becomes one thing is not a decorative mystery placed gently on top of physics. It is woven into the way quantum theory connects with the world that is actually experienced. The theory allows possible outcomes. Measurement gives records. Ordinary life is made from those records, stacked so densely and consistently that they become the stable world of chairs, clocks, footsteps, stars, and very patient measuring devices. The journey began with classical determinism, where reality seemed to have definite properties whether or not anyone looked. Isaac Newton gave physics a universe of forces, motions, paths, and predictable causes. Pierre-Simon Laplace imagined a world where perfect knowledge of every position and motion could, in principle, reveal the entire past and future. James Clerk Maxwell showed that electricity, magnetism, and light could be understood through elegant continuous laws. Measurement looked simple in that older world. A ruler, telescope, clock, or thermometer revealed something that was already there. Then the early quantum discoveries began to disturb that certainty. Max Planck found that energy exchange in blackbody radiation could be understood through discrete packets. Albert Einstein used light quanta to explain the photoelectric effect in 1905. Niels Bohr explained the sharp spectral lines of hydrogen by giving atoms fixed energy levels. These discoveries did not immediately solve the measurement problem, but they showed that the small world was not a smooth classical machine. It behaved in steps, events, transitions, and individual exchanges. The wave function gave this new world its mathematical language. Erwin Schrödinger described how quantum wave functions change over time. Max Born showed that the wave function should be used to calculate probabilities for measurement outcomes. Superposition revealed that quantum systems can be described as combinations of possible states. The double slit experiment showed that those possibilities are not empty bookkeeping, because they can interfere and produce real patterns. Thomas Young's work with light, and later electron diffraction experiments by Clinton Davison and Lester Germer, helped reveal that wave-like behaviour belonged not only to light, but also to matter. The Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg, gave physicists a practical way to use this strange theory. Bohr's complementarity explained why quantum systems can show wave-like or particle-like aspects depending on the experimental arrangement. Heisenberg's uncertainty principle showed that some properties, such as position and momentum, cannot both be perfectly definite in the quantum description. Measurement became the place where a probabilistic description produced one observed result. John von Neumann sharpened the issue through the measurement chain. A quantum system interacts with a measuring device. The device produces a signal. The signal becomes a record. But the device itself is made of quantum matter. This made the boundary between quantum system and classical apparatus difficult to define. Wave function collapse became the name for the apparent transition from many possible outcomes to one observed result. But the meaning of collapse remained open. Schrödinger's cat made that difficulty impossible to ignore. A microscopic uncertainty was connected to a macroscopic outcome, asking where definiteness enters the story. Wigner's friend pushed the puzzle further, asking how different observers and records fit into the same quantum description. These thought experiments were not designed to make physics spooky for its own sake. They were ways of exposing the tension between quantum possibility and ordinary definite experience. Decoherence gave a powerful modern explanation for why everyday objects look stable and classical. H. Dieter Zeh and Wojciech Zurek showed how interaction with the environment can make interference between quantum alternatives effectively inaccessible. Air molecules, photons, heat, dust, and surrounding matter can all carry away information. Quantum Darwinism, developed by Zurek, goes further by suggesting that the environment spreads many copies of information about stable pointer states, allowing many observers to agree on the same ordinary facts. Then the interpretations offer different answers to what is really happening. In many worlds proposed by Hugh Everett, and later popularized under that name by Bryce DeWitt. The wave function never collapses. Every possible outcome continues in a different effective branch, while each observer experiences one definite result from inside one branch. In Bohmian mechanics, developed from Louis de Broglie's pilot wave idea and expanded by David Bohm, particles have definite positions all along, guided by a real wave-like structure. In objective collapse theories, including the Ghirardi-Rimini-Weber theory, collapse is treated as a real physical process that makes large systems naturally definite. Roger Penrose has also suggested, more speculatively, that gravity may be connected to collapse. Modern laboratories show that measurement is not only a philosophical question. It is a precise physical practice involving detectors, entanglement, environmental interaction, repeated trials, and recorded information. Alain Aspect, John Clauser, and Anton Zeilinger helped test the foundations of quantum theory through Bell inequality experiments. Institutions such as the National Institute of Standards and Technology, the University of Vienna, and CERN continue to use measurement at the edge of quantum precision, particle physics, and controlled quantum systems. The question remains unresolved, not because quantum physics is weak, but because it is so successful. The predictions work with extraordinary accuracy, while more than one deep interpretation remains logically possible. The safest factual conclusion is that measurement involves real physical interaction, information transfer, environmental entanglement, and stable records. The exact meaning of collapse depends on interpretation. Reality becoming one thing is not magic. It is not human imagination commanding matter. It is one of the most precise and carefully studied puzzles in science. Perhaps the definite world is what possibility looks like after it has touched enough of the universe to leave a trace.